All right, today we are going to dig into a question that on the surface makes absolutely no sense. Why are the biggest, most massive ships on the ocean also some of the fastest? The answer, it turns out, is just some really beautiful physics.
I mean, this is the heart of the puzzle, right? It just feels wrong. You think a smaller, lighter boat would be way more nimble, way quicker than some colossal ship that's displacing thousands and thousands of tons of water. But surprise, on the open ocean, that's not how it works at all. And we're not talking about a small difference. It is huge. A 400-meter container ship, it'll cruise all day at 25 knots. A much smaller 100-meter ship might be maxing out around 15 knots. So what in the world is going on here?
Yeah, we're calling this the big ship paradox. It flies in the face of our intuition, you know? Everything we know tells us that bigger and heavier should mean slower. But as we're about to find out, the ocean kind of has its own rulebook.
And the solution isn't just about cramming a bigger engine in there or using more brute force. Nope. It all comes down to the way a ship physically interacts with the water it's moving through. The real secret is in the waves. So let's talk about making waves, because every single ship, I don't care if it's a tiny little rowboat or a giant supertanker, is basically a wave-making machine. And understanding these waves is the absolute key to solving our puzzle. So think about it. As a ship's hull cuts through the water, it's pushing all that water out of the way. This creates a little mountain of water, a peak, right at the bow. Then, at the back, the stern, water rushes in to fill that empty space, creating a valley or a trough. So the ship is always sailing inside this little wave system that it creates all by itself. Now this is the part you really gotta lock in. The speed of these waves is exactly the same as the speed of the ship. They're tied together. So what happens when the ship speeds up? Well, that distance between the peak at the front and the trough at the back, it stretches out. The wavelength gets longer. This one simple relationship is the foundation for everything that comes next. So because speed and wavelength are locked together, it creates this kind of natural speed bump for any conventional ship. It's a physical barrier, and it has a name: hull speed.
So, what is hull speed? Well, it's the point where a ship is moving so fast that the wave it creates is exactly as long as the ship itself. The ship literally gets trapped, with a wave peak at the bow and the next peak right at the stern. It's like it's trying to climb a continuous, never-ending hill of water, a hill that it made itself. This creates a massive wall of resistance.
And believe it or not, there's actually a pretty simple formula that helps us figure this out. This right here is the key that unlocks the whole puzzle. The hull speed in knots is about 1.34 times the square root of the ship's length at the waterline, measured in feet. And the most critical variable here isn't weight, it isn't width, it is length. And this is where we have our aha moment. Because when we actually start plugging numbers into this formula, we see exactly why a longer ship has a much, much higher top speed. Just look at these numbers. A little 20-foot pleasure boat hits its wall of resistance at just 6 knots. A 300-foot commercial ship can get up to 23 knots before efficiency just tanks. And then you have the massive Queen Mary 2. At over 1,100 feet long, it has a theoretical hull speed of a staggering 45 knots. The longer the ship, the faster it can go before it starts fighting its own wave. So here's the crucial takeaway. A bigger ship doesn't have to work as hard to go fast. The physics of how waves are made just mean its natural speed limit is, well, it's just higher. It can cruise at speeds that a smaller ship would find physically and economically impossible to overcome. Now you might be asking, can you beat this limit? And the answer is yes. But it is not easy. It takes some really clever engineering and a whole lot of power. If you just pour on the power to try and push past your hull speed, you enter something called hump speed. The stern of the boat sinks down, the bow points way up, and you're literally trying to climb a hill of water. But if you can break through that barrier, a vessel can get on plane, and that's when it's skimming across the surface instead of plowing through it. And this explains exactly why our huge container ships can't just act like a speedboat. They have displacement hulls, which are designed to plow through the water as efficiently as possible. They simply can't generate the kind of power needed to get over that massive hump speed and start planing. They're built to live their lives below their hull speed. But engineers have other tricks too. You've probably seen that strange-looking lump on the front of many big ships. That's a bulbous bow. It's designed to create a second wave that's perfectly out of sync with the main bow wave. And when they meet, they basically cancel each other out, reducing drag. Another trick is just to use long, thin hull lines, which slice through the water more gently and create less resistance from the get-go. Okay, so let's bring all this home. Let's circle back to that original question and lay out the final clear answer. So here it is. Big ships are faster not because they have more powerful engines, necessarily, but because the physics are just on their side. Their sheer length raises their natural speed limit, which allows them to cruise efficiently at speeds a smaller ship could never hope to sustain.
To put it simply, a small ship hits that wall of water resistance at a much lower speed. But a big ship, thanks to its super long waterline, just pushes that wall much, much further down the road. And that gives it a higher, more efficient cruising speed. It's really as simple as that.
And that leaves us with a pretty fascinating thought, doesn't it? If a ship's speed is so fundamentally tied to its length, what does that mean for the future of high-speed travel on the water? Are we going to see even longer, thinner ships? Or will some radical new hull design finally let us break free from the limits of the wave altogether?